On the left, we have a second-order differential equation, y double prime plus by prime plus ky equals 0. On the right, a tidy matrix equation, u prime equals au. These two statements say exactly the same thing. The bridge between them, the companion matrix, is one of linear algebra's most elegant tricks. Let's see where that matrix comes from. We start with the second-order equation, y double prime plus by prime plus ky equals 0. Linear algebra handles first-order systems beautifully, matrices times vectors. But this equation has a second derivative in it. Our goal is to force this single scalar equation into the shape u prime equals au, where u is a vector and a is a constant matrix. Here's the key move. Name the derivatives. Define the vector u with two entries, y prime on top and y on the bottom. Each derivative of y that appears in the equation gets its own slot in u. Put the highest derivative on top. That choice matters. It's what will make the original ODE's coefficients land neatly in the first row of our matrix. Reverse the order and you'll get a different, uglier matrix. Order here is a convention, but it's a fixed convention. Now let's differentiate u. The derivative of the top entry, y prime, is y double prime. The derivative of the bottom entry, y, is y prime. So u prime is the column vector with y double prime on top and y prime on the bottom. Next, we rewrite each component using only y prime and y, the entries of u. For the top entry, we solve the original ODE for y double prime, which gives negative by prime minus ky. For the bottom entry, y prime simply equals y prime, a trivial identity. Both entries are now linear combinations of y prime and y. Now let's package these two linear combinations as a matrix times u. The matrix A has first row negative b, negative k, and second row 1, 0. So u prime equals A times u, where A is the 2 by 2 matrix with top row minus b minus k and bottom row 1, 0. Notice that row 1 is physics. It came straight from the ODE. Row 2 is bookkeeping. It just came from the definition of u. As a quick sanity check, with b equal to 3 and k equal to 2, A becomes the matrix with top row minus 3, minus 2, and bottom row 1, 0. Multiplying gives u prime equal to minus 3y prime minus 2y in the first component and y prime in the second, exactly as expected. This trick doesn't stop at second order. Take a fifth order equation, y to the fifth plus a 4 times y to the fourth, plus a 3 times y triple prime, plus a 2 times y double prime, plus a 1 times y prime, plus a 0 times y equals 0. Define the vector u with 5 entries, y to the fourth on top, then y triple prime, y double prime, y prime, and y at the bottom. Highest derivative on top, descending. Now differentiate. The top entry's derivative is y to the fifth, and the ODE tells us that equals minus a 4 times y to the fourth, minus a 3 times y triple prime, minus a 2 times y double prime, minus a 1 times y prime, minus a 0 times y. Every other entry's derivative is simply the entry sitting above it. The second slot becomes y to the fourth, the third becomes y triple prime, the fourth becomes y double prime, and the fifth becomes y prime. Once again, a single high-order equation collapses into a first-order system. Assembled, this is the 5 by 5 companion matrix. The top row holds the ODE coefficients, negative a4, negative a3, negative a2, negative a1, negative a0. Below that lies a subdiagonal of 1s, and every other entry is 0. The pattern is universal, one physics row coming from the ODE itself, plus n-1 identity rows that each simply say a derivative equals itself. A quick warning here. We haven't added any new information. The trivial equations don't impose new constraints. They just unpack the higher derivatives into named variables. Same solutions, just dressed in new clothing. Here's why this matters. Let's compute the eigenvalues of the matrix A in the 2x2 case. We form A minus lambda times the identity and take its determinant. The matrix has top row minus B minus lambda minus K and bottom row 1 minus lambda. The determinant is minus B minus lambda times minus lambda minus the product of minus K and 1. That simplifies to lambda times B plus lambda plus K, which is lambda squared, plus B lambda plus K. Setting this to 0 gives lambda squared plus B lambda plus K equals 0. Notice something remarkable. This is literally the characteristic polynomial of the original second order ODE. Now plug in B equals 3 and K equals 2. We get lambda squared plus 3 lambda plus 2 equals 0, which factors as lambda plus 1 times lambda plus 2. The roots are lambda equals minus 1 and lambda equals minus 2. These are exactly the exponents you would obtain from the classical ansatz y equals e to the lambda t applied directly to the original differential equation. The eigenvalues of the companion matrix are exactly the characteristic roots of the ODE. It's the same computation expressed in two different languages. And this is why linear algebra is the natural language of linear dynamics. Next, we'll diagonalize A and watch the classical solution e to the lambda t fall straight out.